Hi everyone, in the previous molecular fingerprints video, I have a link over here if you don't know what I'm talking about. We saw how to generate molecular fingerprints and use them for structure search. In this video or in this notebook, I'll use Avalon fingerprints. So these are the three different types of chemistry problems that we are going to model using machine learning and Avalon fingerprints as a molecular descriptor. We'll see the HOMO-LUMO energy gap of organic compounds, yield prediction of the carbon-nitrogen cross-coupling reaction, and the third type of problems that we are going to see is the catalytic enantioselectivity of thiol-imine reactions. We'll encode molecules using Avalon fingerprints, and then we'll use machine learning models, specifically random forest and light GBM regressors. And using these machine learning algorithms, we'll develop predictive models for HOMO-LUMO energy gap of molecules. HOMO stands for highest occupied molecular orbital. LUMO stands for lowest unoccupied molecular orbital. So we can develop predictive models for this HOMO-LUMO energy gap of molecules using Avalon fingerprints. Similarly, using these Avalon fingerprints, we can develop predictive models for reaction yield and enantioselectivity. As usual, we need to import these libraries. The first one is pandas, numpy, seaborn, matplotlib. These are already kit libraries, and also we need scikit-learn. These are the libraries that we need for scikit-learn, and also we need to import light GBM regressor. Let's run. Just to run the cell, you need to press Shift plus Enter. Okay, so we are imported the libraries. First thing we are going to see is a HOMO-LUMO energy gap of molecules. The dataset is obtained from this publication, so there is a link over here. You can read the original paper. So let's import the CSV file. So you can see here the CSV file contains smile strings and energy gap of the molecules, right? So if you look at the shape to see the total number of compounds, we have 2,904 compounds, and we have two columns, smiles and the energy gap. So the first thing we need to do is we need to include the structure of the molecules by creating a new column, the structure column, using this Panda tools add molecule to frame. So you need to pass the data set, this one, and you need to tell the smile column, right, smiles, and then this is a new column that contains the structure. So let's run and see. Okay, so we have added a new column contains the structure of the molecules. So we'll use this column to calculate Avalon fingerprints of the molecules, right? So I already wrote a function over here to generate the Avalon fingerprints. So the number of bits that we need to generate is 4096. Usually if you generate smaller bit lengths, there is a possibility of bit collision. So to avoid that, this 4096 is enough for these molecules. So let me run the function first, and then function call. Here is the function. So this is the data set contains, we are passing the structure of the molecules. We are passing, okay, we are passing this column, this is the structure column. We are passing the structure column for the function to calculate the Avalon fingerprints. So let me run this. You can see the columns. How many columns do we have? It may take some time. So we have 4096 columns, right? These are the number of columns, meaning we have 4096 features. We need to instantiate the models, light GBM. Number of estimators in this case is 800. That works the best. Random forest, the default value is good. So let me run this cell. Now we need to perform tenfold cross validation, right? So I put a time here just to see how long does it take. From scikit-learn, we need to use shuffle split. Number of splits, 10 splits. Test size 0.3, which means in each fold 70% of the data will be used for training and 30% of the data will be used for testing. Okay, so for scoring we use R squared, which means coefficient of determination, and negative mean absolute error. Okay, so these are our scoring. So to perform the cross validation, you need to use cross validate, right, which is found in scikit-learn. So cross validate, this is a light GBM model. These are the fingerprints, the Avalon fingerprints, which are the features for the molecules, and then we need to pass the Y value. This is a Y value, which means the energy gap. Scoring, for scoring we need to pass this scoring over here, so you'll have R2 and negative mean absolute error. For cross validation you need to pass this one. Okay, that's it. The other ones are just time. It doesn't take that much long. Let me run this cross validation and see the results. A tenfold cross validation. Yeah, it's done. So you'll get this kind of information. So if you look at this, it might be a little bit confusing. This is a dictionary. So what we need is we need test R2. Test R2 is this one. So this is the key. The values are this array, right? So these are the values. The other thing we need is test negative mean absolute error. So this is a key, and the values are this one. Okay, so how do you access that? We have a variable scores val, and then if you put the key over here, you can access the values. So these are the values. If you say test R2, to get the mean absolute error, you have to use scores test negative mean absolute error. If you put negative here, the values becomes positive. So if you look at the values over here, they are negative, so we want to make them positive. To make them positive, just put a negative sign over here, so everything becomes positive. Okay, so they become positive values. So what we need is the average values, the average value of R squared and the average value of the mean absolute error. Calculate that, just you have to use the numpy mean. So we got R squared 0.91 and mean absolute error 5.92. So if you compare this with publication, so they used similarly 70-30 split, tenfold cross validation, but they used a different fingerprint. They call it multiple fingerprints. I believe they used 24 fingerprints to get this result. So from their result, if you compare, our results are slightly better, at least. This is 0.91, this is 0.89. If you look at the error, our error is 5.92, theirs is 6.26. So we got slightly better results just using simply Avalon fingerprints. Yeah, so it looks good. We got good results. Split the data 70-30%. Okay, so if you look at just a simple 70-30 split, 70% of the data for training, 30% of the data for testing. Yeah, the error is 5.79. okay, that's good. So the second problem that we are going to see is yield prediction, the carbon nitrogen cross coupling reaction. So here is the original paper. So what they did in this paper was they did carbon nitrogen coupling reaction. So they used, these are the aerial halides. They used 15 different types of aerial halides. So there is one, 15 different types of aerial halides. They also use a catalyst, this one, and the catalyst, they vary the ligand. So there were 4 different ligands, 1 2 3 4, right? The other thing they used was additives. They used these 23 different additives, and also they used 3 different types of bases. These are the bases, the 3 bases. So total, if you calculate the number of variables, 15 times 15 is the number of aerial halides, times 3 bases, times 23 additives, times 4 ligands. So you'll have 4140 possible reactions. Okay, so how do you do all these reactions? This is not an easy thing. So they used high throughput experimentation to perform these reactions. Let me see what this plate look like. So they used a plate like this. So they did reaction on, okay, in each well. These are the wells. So this is 1536 well plate reaction. So they perform a reaction like this, or they use three plates to perform all the reactions. Okay, 3 plates to perform all the reactions. So that's what they did. From that, they removed the control reactions and one of the additives. So totally they used 3960 reactions for machine learning. They determined the yield using UPLC, using an internal standard, in this case diterbutyl biphenyl. Okay, that's their internal standard. So in that way they got the yield of the reaction. For the descriptors, they used density functional theory. This is a known method for density functional theory. So they calculated descriptors of all the 4 variables using density functional theories. So for additives, they calculated 19 descriptors. For aryl halide, they calculated 27 different types of descriptors. For base, 10 different types of descriptors. And for a ligand, they calculated 64 descriptors. Okay, so using these descriptors, they developed a machine learning model, and finally the best model they got from 70-30 split was a random forest model. The coefficient of determination was 0.92 and root mean square error was 7.8. Now let's use their data. Let's use just fingerprints to develop a similar model. So this is their data, which is obtained from this reference. Okay, so we have the ligands in the ligand columns, additives, base, aryl halide, and finally you have the yield. So we'll calculate fingerprints of the ligand, additive, base, and aryl halide, and then we'll concatenate them. If you look at the structure of the additives, base, and aryl halides, they are kind of small. Okay, they are small molecules, but if you look at the ligand, at least they are bigger. The length should not be the same as that of the aryl halides, because these aryl halides or these additives, the structures are just small, but the ligands are bigger. So we need to assign bigger bit size for the ligands. That's why I used 2048 for the ligand. For the other, just I used 1024 for the bit length. Okay, so I'll calculate the fingerprints of the ligand, additives, base, and aryl halide, and then I'll concatenate them using NumPy. It may take some time because we are calculating fingerprints of 4 different variables. So here I'll concatenate the fingerprints of the ligand, the additives, base, and aryl halide. This is just concatenation. Okay, it is done. So when we concatenate all this, the number of columns becomes 5120. These are the number of data points. Okay, now using these fingerprints, this is just a number of columns. To show you the number of columns, we can give column name. So we have 5120 columns. And now we can do tenfold cross validation to see the results. 70-30 split, just similar to what we did before. So we need to pass the concatenated fingerprints, and then we need to pass the yield. This is the yield. So we need to do tenfold cross validation, and this is the results. Okay, and compare the results with published data. Okay, it may take some time. It's done, right? So now let's access the coefficient of determination. Using the key, you can access the values. These are the values. This is the coefficient of determination, 0.95. Okay, Similarly, let's take the average values, because we need to compare the average with the published data. Okay, so we got coefficient of determination 0.95 and the root mean square error 6.06. Now let's compare with original paper. The original paper is a duals paper, which is 0.92 r squared, which is our case is much better. They used multiple fingerprints in this paper. They got 0.93. Still ours is better than what they got. Root mean square error, if you look at the original paper, the root mean square error is 7.8. In our case you have 6.06, which is lower. The smaller error is a better, so this one is better. Using these simple fingerprints, you can even get better results than published papers. I'm really surprised with that. So let's do some split and just do one single shot, training 70% of the data and 30% of the data for test, and then if you plot that, you'll get kind of similar results with the average, right? 0.95 root mean square error 5.91. This is just simply Avalon fingerprints. But as I said in the publication, the original publication, they used descriptors obtained from density functional theory. In this paper, they used multiple fingerprints to get 0.93, but we just use a single Avalon fingerprints to get 0.95. In fact, in this case they used random forest. In this case we used light GBM, so the algorithms are different. That may be the reason, or maybe the descriptors may be the reason. So anyways, we got better results than the published data. That's really great. Okay, so the last type of problem is prediction of enantioselectivity. So this is also a published paper. In this reaction you will have an electron deficient imine here, and here you have a nucleophile. This is electrophile, this is a nucleophile, which means this nucleophile can react with an electrophile. This nucleophile has two possibilities. It may react from the top side or it may react from the bottom side. If it reacts from the top, you'll get one isomer. If this reacts from the bottom, you'll have the other isomer. So these two isomers, we call them enantiomers. In the absence of a catalyst, you'll have a 50-50% chance, so that you'll have 50-50% mixture. We call it racemic mixture. But due to the presence of a catalyst, the catalyst can create kind of bias. So it creates selectivity from, if the, say for instance, if the catalyst binds from the bottom, the nucleophile only attacks from the top, something like that. So you'll have enantioselectivity if you use a catalyst. Now the question is, can we really predict enantioselectivity using machine learning? So in this reaction, the original paper, you can read it from this. They used 5 imines, 5 thiols, and 43 different catalysts. Okay, phosphoric acid catalysts. And if you multiply this 5 times 5 times 43, you'll have 1075 possible reactions. So these are the total reactions. They did these reactions, and then they calculated descriptors for the catalyst, and they predict enantioselectivity. Okay, so that's the original paper. In the second paper, they used multiple fingerprints to predict yield, but in this case we will use just simply Avalon fingerprints to see if they can predict enantioselectivity. So first let's import the data. So what we'll do is we'll calculate the fingerprint of a catalyst, imine, and thiol, and then we'll concatenate these fingerprints, and then using these concatenated fingerprints we'll predict the enantioselectivity. This is the enantioselectivity. So let's calculate the fingerprints of each input, which is catalyst, imine, and thiol. If you look at the structure, the catalyst is bigger, so that's why I increased the number of bits for the catalyst. For the imine and the thiol, 1024 is enough. So if you do that, let's see, and then we need to concatenate. the fingerprints. Okay, so we have 1075. These are the number of data points, so these are the number of columns, right? And then we can put it in a data frame. Okay, so these are the number of columns and number of rows. Okay, so we do this shape. Now let's do tenfold cross validation. In this case, we'll split the data for 600 for training, 475 for testing. So otherwise it's the same. Tenfold cross validation. Let's see the results. In this case, we'll use random forest, right? Previously we used light GBM, but in this case random forest seems better than light GBM, so that's why I'm using random forest regressor. It may take some time. So in the meantime, I can show you the results. So in the original paper, the split is 600 for training, 475 for test. In the original paper, we have 0.152. In the second paper, which is this one, they go 0.114 for the mean absolute error. So we got the results now. So if you look at R squared is 0.9, we don't have R squared over here, but the mean absolute error is 0.146. So in the original, the smaller is the better usually. So if you look at the original paper, it was 0.152. In the second paper, which is in this link, so in that case they used multiple fingerprints, so 24 different types of fingerprints. They go 0.144, 0.146, the same as somehow these multiple fingerprints. So from this we can say that these Avalon fingerprints can predict, 3 different types of chemistry problems. Okay, the HOMO-LUMO energy gap, the carbon-nitrogen cross-coupling reaction, yield prediction from carbon-nitrogen cross-coupling, and also enantioselectivity. There is a practice problem over here, so if you are serious to learn machine learning chemistry, so you need to work on this practice problem. In summary, using Avalon fingerprints as an example, we have developed predict models for 3 different types of chemistry problems: the HOMO-LUMO energy gap, reaction yield, and enantioselective reactions. Hopefully in the next video I will show you how to combine results obtained from machine learning and molecular docking to identify potentially active compounds. Stay tuned for that. If you like this video, please subscribe the channel. Thank you.